Welcome to our last tutorial of the GCEP Symposium, and it's a special one, and it's my special privilege to introduce Chris Edwards, who has had a distinguished career at GCEP. He was the inaugural Deputy Director of GCEP for 3 or 4 years, and then was a research team leader, and has been a PI, I would say, almost throughout the whole time of GCEP. And I had the pleasure of working with Chris for the first few years, and you know, when I worked with Chris, I was impressed by the energy he had, and you know, even in the chaotic environment that we had at GCEP, we still managed to get some work done. So I'd like to thank Chris for his energy, his entropy, and his exergy. And that is actually, I'm sure you'll hear a few puns from Chris, so he'll certainly outshine me on that. So, you know, throughout the whole time here, I've always really wanted to know what Exergy is, and I'm sure many of you have, and you've heard lots of Chris's presentations, and you've all been dazzled by them. So today, we have the opportunity to learn Exergy 101 from Chris. And so with that, you know, Chris, for those of you who don't know him, he's a professor of mechanical engineering here at Stanford, and is working on a couple of GCEP projects. He completed his master's and PhD degrees at University of California in Berkeley, and spent several years at Sandia before coming here to Stanford. So with that, Chris, thank you very much.
Okay. Let me start out by letting a little hot air out of the balloon here. There's nothing magical about Exergy. This is just sort of the next step in thermodynamic analysis, and not even next step with respect to, you know, discovery or, you know, it's so exciting. It's just the next step in what you do in combining the first law and the second law. So in fact, if you look at an undergraduate textbook in Thermo, chapter 6, 7, 8, one of those is going to be an Exergy chapter, or availability. Availability is the MIT term, the European term is Exergy, they're the same thing, right? The difficulty is Exergy or availability is the combination of the first and second law, so that you can move away from this conserved quantity, which is energy, and you can figure out what the valuable part of the energy is, what the equivalent of the gold standard is, which is work, how much work you can get out of this, right? And it's a little tricky when you're teaching undergraduate thermo, because it takes a while to get a handle on the first law, and by the time you got the handle on the first law, you're struggling with the second law, and then by the time you got a handle on the second law, you're out of the class, right? And so that's a little bit tricky. You can construct a class, or maybe do another class where you come back and you put those two together, so you're feeling a little bit better about that. But if you do that, then you don't get to chemical exergy. You'll get to what's called thermomechanical exergy, so you understand that heat at different temperatures has very different values between the two. But you won't get to chemical, and unfortunately our energy system runs primarily on chemical energy. So what happens is you then do chemical thermo, reactive thermo, you do chemical equilibrium, you do mixtures, you do vapor-liquid equilibrium, all this stuff, and you keep putting this thing off until you get to graduate school. And so that's sort of what's happened. And that's actually unfortunate, because it turns out that the easiest way to think about energy systems, and for sure the best way to optimize them, is in terms of exergy. Things that seem a little strange or mystical or, okay, great, that's what I got, but what do I do about it, actually just become much clearer. But there's really nothing mystical about this. So I'll talk with you a little bit about that today. As a way to start, maybe we'll start out with a question. Which resource would you choose? I'll give you two choices, 2 tanks. Big tank, it's got 1 kilogram of air, it's at 1 bar, it's at 20 degrees C. Or a tank where I half all the dimensions, 2 cubed is 8, so it's at 8 bar, it's got the same mass of air, it's at 20 degrees C, but higher pressure. Which is a more valuable energy resource? Oh, I love that. Hold that thought. Before that, I'll give you the hint. They both have exactly the same amount of energy. So air under those conditions is an ideal gas. The internal energy is a function of temperature only. So they have the same energy inside of both. Which would you rather have given where you are?
The 8 bar.
You'd rather have the 8 bar. Why would you rather have the 8 bar?
I live in a 1 bar environment, so I can utilize the difference.
Well, how would you utilize it?
Take the air and run it through a turbine.
Yeah, that would be a great way to do this. What if you live in an 8 bar environment?
Take the 1 bar.
What would you do with it?
Same thing, went the other direction.
You're banned from answering questions. Okay, all right, okay, we're fine. I'm going to take the 1 bar tank and I'm going to change it to methane. Which would you rather have?
What's my bar?
You live here.
Take the method.
I'm going to take the methane and I'm going to start diluting it with air. I'm going to keep diluting it with air. All right, forget that one. I'll put the methane inside that tank. We've got the 8 bar environment. I'm going to change the environment to a planet that's at 8 bar. And the environment's made out of methane. Which would you rather have? You'd rather have the air back at the 1 bar. Okay, so there's a couple of things. Your point, you took my thunder right from the beginning. Not that it's great thunder. The ability to get work from a resource depends upon the resource and the surroundings that it's in, right? So the idea that you probably got somewhere along in high school that energy is the ability to do work is just not correct. That's not what energy is. That's actually what exergy is, right? And it's a property both of the resource and the surroundings in which you sit. Not too surprising. Okay, Richard, were you looking at my slides? Okay, so I've been preempted on this thing, but I'm going to give you a few definitions. In terms of assumptions, I'm going to assume that you know thermo, or that you had it once upon a time. Okay? This is a tutorial, and it's a tutorial on exergy, so I'm going to show you how to derive this stuff. And that's okay, we'll knock a little rust off as we go. So first, energy is not the ability to do work. Energy is actually a tricky thing to define. Everybody thinks they know what energy is, okay, but if it's not the ability to do work, what exactly is it? You look in a thermo book, you won't find it defined. You go to a high school book, it's defined, the ability to do work. That's wrong. If you look at a college level book, it will say something about the ability to cause change in the world. And I mean, it's wonderful and aspirational, and so I love the definition. On the other hand, I hate it because it's completely non-technical, so you can't really do anything with it. So the best definition I can give you, it's the extensive conserved quantity that is interconvertible with heat and work. Now that's a little dry, I know. And you might say, well, geez, how do you separate energy from the first law, which is the conservation principle? And the answer is it's not separable. So work was defined long before energy in terms of Newtonian mechanics. Heat transfer was defined long before energy was. And it wasn't until Joule came along and said, hey, what about this equivalence between heat and work? And still didn't quite have his finger on the fact that there was a conserved quantity, and there was a very distinct sign between the two in terms of work could go to heat. Heat could not completely go to work. But there was something in between there that was storable. And so separating the storage from the transfers was tricky. Well, if that's energy, how about entropy? Entropy is the extensive measure of the number of microscopic rearrangements of energy. S equals K log omega. What on earth does that mean? I have a system, it has a certain amount of energy. If I can go in with that and microscopically rearrange it in omega possible configurations, the logarithm of omega multiplied by Boltzmann's constant is a little 0 point thing that hangs out on the side, don't worry about that, from it, is the entropy. The logarithm is forced from the fact that it has to be extensive. That if I have energy in system A and energy in system B, then the combined system of A plus B is the energy, sum of the energy of the two. The entropy also has to be the sum of the entropy of the two. And that absolutely forces the logarithm. That's the only form that it can take. Right? So it's a measure of microscopically how many ways I could rearrange it. If I took, I don't know if you can see this or not, I don't have my glasses on. The little boxes there, think of those as being atoms, and each atom can have a quanta of energy or not have a quanta of energy. So the little subset where there's 9 atoms with little x's inside of it, if I put all the energy in that central region, 9 units of energy on those 9 atoms, how many possible rearrangements do I have of 9 units of energy in 9 atoms? There's only one arrangement, there's no rearrangements for that. But if I take one out, now I can move the gap around to 9 different places. And I can take the one that I pulled out and put it in 27 different places. 9 times 27, many more rearrangements when that first unit goes out. That's the first step after the Big Bang. Energy is now wandering and beginning to disperse in the universe and finding more and more rearrangements, and entropy is going up. What it will mean for us is that the better organized the energy, the fewer options it has for rearrangement microscopically, the easier it is to take for a ride. I can make it go where we want. You wanted the high pressure tank because you could connect it to a turbine, make it go through that turbine. right? If it was not organized in that tight tank, I couldn't do that. If I just put the turbine in the room here, go through my turbine. Some air is going to diffuse through the turbine, right? But the odds are as much air diffuses the other way along. So it's not really going to be a basis of a startup company. Okay, so that's what entropy is about. And we already got to the third point. Exergy is the potential of an energy resource to do work in a given set of surroundings, aka an environment. And that's what we want to go after. Okay, so I'm going to do this from the ground up. So we're going to talk about a resource in contact with an environmental reservoir. So this is some sort of an energy resource. If you want to be concrete about this, it's methane. It's a kilogram of methane. Okay? I put it in contact with an environment. Think the atmosphere. Right? And it's only the existence of those two that makes that a valuable resource, right? An energy resource. I have to permit interactions between them, so I'll permit interactions of matter exchange, heat exchange, and work, boundary work. It can dilate. And what I want to know is how much work can I take from this system? How much can I take for human purposes, right, from it while interacting with the environment? So what I'm going to assume is that the reservoir that I interact with, the environment, is large but finite. What that means, if it's large but finite, it means the intensive properties during my interaction are not going to change. They're essentially fixed. But I am transferring things to it. So if I do this long enough, there'll be an integral. There'll be a price to pay. Does that sound like CO2 accumulation in the atmosphere? Okay, it's part of that. The reservoir has fast internal transport, and you should be uncomfortable about that. I'll explain that. What that is I'm forcing all entropy generation to be inside of the system. So by fast transport over here, think of this as I have this surroundings, but it's really mixed up so that the temperature of that boundary stays at the temperature of the environment, the chemical potential stays at the chemical potential of the environment. I've basically forced it there. Now that's not really reasonable, right? But if we do the alternative, what the alternative is, I have heat transfer, I have an affected zone that grows in the environment that I generate entropy in, and then when my process is done, it will grow back to this boundary, and we attach an auxiliary system onto this, and we track it back and forth. I can do the same thing by imposing the conditions at this boundary and forcing the entropy generation inside of my system boundary, so the affected zone has to occur in here. What I'm doing is forcing the resource, and whatever system is manipulating the resource, to meet the environment on its own terms, to take the irreversibility inside. You okay with that? It just simplifies the math. But we can do it either way. Okay, that makes the boundary properties fixed. We force the irreversibility into the system. If I write the first law for this, so for the resource, the change of internal energy goes up due to heat transfer, it's going in, delta Q, goes down due to boundary work. If it pushes against the environment, I'm losing energy from it, delta WB. Goes up due to transfer of species, delta Ni, a small transfer, mole number, Ni, species I, going in, carries an enthalpy per mole, H, and it goes down due to the work that I'm going to take out of the system. You okay with that? Not okay with it?
Because you're skipping about steps.
There's no step skipped on that balance.
Well, you brought an enthalpy in the energy balance, and there's never defined enthalpy and why it's enthalpy.
Oh, come on, you know what enthalpy is. No, so the predicate statement is unothermo. So enthalpy is U plus PV. It's the transfer of energy with matter, right? Yeah, it is. So, but challenge me on anything you like, but that's covered.
Well, I actually meant something slightly deeper as well.
Yeah.
You've got a hidden meaning there at the bar on the top.
That's per mole.
It's also partial molar intensity there, or?
Yes, because I'm transferring per mole. So N is a molar transfer. If I take the bar off, it's per mass, so that'd be a delta M.
No, what I meant is the partial molar enthalpy in the sense that it's a multi-component system with the
Absolutely. So it is the enthalpy carried by that particular species in its mixture. It's completely general. It's completely general. Okay, and for any species, if I do an entropy balance for this, the change of entropy inside the system goes up due to heat transfer, an amount delta Q on T, temperature of the boundary, goes up because matter comes in and it carries entropy with it. So that's S bar per mole times the molar transfers for the species. And I can make entropy inside. So if I do something that causes my energy to become less organized, have more rearrangements, I burst a diaphragm inside and let it double its volume, unrestrained. That generates entropy, more rearrangements in the system. Okay? Okay, what I'm gonna do is take this Q, solve this for Q, stick it in here, and rearrange for W, which is what I want out. We want the work that we can get from this. That's what Exergy is gonna be. If I do that, I have the bottom line. So the differential amount of work comes at the expense of the internal energy. I don't get to use any pushing on the boundary. That's interacting with the outside world. I can't use that. I could get a freebie if I have heat transfer coming in. If this was cold, for example, I get a little extra. The only part I get of that enthalpy is the enthalpy after I pay the entropy tax. So H minus TS, which is the chemical potential that's brought in with the species. And then I'll pay a tax if I generate entropy inside of it. And notice that tax is T naught delta S gen. That's the destruction of Exergy. That's the lost opportunity to do work. Okay, if I take that and I say I want it to be as good as it can be, Exergy should be the potential, not what I actually get, but what could I get? What's the best I could ever do? The best I could ever do, this term by the second law has to be 0 or positive. Now in reality, it'll be positive. For anything that actually happens, it'll be positive. That's an intrinsically positive quantity. It's got a minus sign in front. The best I can do is to set that to 0, because otherwise this will always cut into the work I can get. Now what I have is the reversible work for the system, given by what remains on the right-hand side. Okay. I'm going to make one more shift. The one more shift is, rather than saying any species K, I'm going to say that I only get to transfer environmental species with the atmosphere. And the reason for doing that, I mean, you know that I could, so what are environmental species in the atmosphere? Oxygen, nitrogen, argon, helium, water, CO2, things that naturally occur in the atmosphere. You know that I could transfer tungsten. I mean, all kinds of crazy things, right? Would it be a good idea? Probably not a great idea to do. I'm going to restrict this to environmental species because it will make it mathematically easier. But for those who want to do it the other way around, first I'll tell you how you do it. And second, I brought a paper which derives it the other way around for arbitrary species. The short version of the story is that if I have something that is not present in the atmosphere already and I transfer something to it, the chemical potential I transfer to is negative infinity. And that makes it a little tricky for the math. But that's actually an integrable singularity, and the back side of the paper integrates that. So we'll get to exactly the same place, but it's a bad idea to take species not in the environment and transfer them to the environment. So for now, I'll make it mathematically simpler and do just environmental species across it. Okay? Okay, we'll get to exactly the same place at the end. All right. So I've got this resource, and we were thinking about this as being a tank of methane, right? I've got this thing of methane. I want to know how much work I can get out of it. Well, the methane, we choose something crazier, isooctane, right? We should not have isooctane in the atmosphere. Well, you could debate about methane in the atmosphere, right? Natural sources for that. Isooctane should not be in the atmosphere. So in order to do this, I need to react reversibly, because I don't want to have entropy generation. It'll cost me work. I need to react that isooctane reversibly to atmospheric species. Now that's not that tricky, right? The carbon should go to CO2, the hydrogen should go to H2O, naturally occurring species from it. So what I'm going to need is a chemical reaction that will transform all resource species J to species naturally present in the environment I, whatever they may be. I can do that by writing a transformation reaction. If this is my J species, this is isooctane, by some stoichiometric coefficient isooctane plus some amount of oxygen, making CO2 and making H2O. A plus B goes to C plus D. Just a generic reaction. A generic transformation to environmental species. That's the key. If I rearrange that, we sometimes do this to make things more general. We'll do what are called signed stoichiometric coefficients. I'm going to take this partner reactant, whatever it may be that I need to make the transformation, and I'm going to put it on the other side of the transformation arrow and put a minus sign on it. because it's now on the wrong side of the transformation. So isooctane plus negative B oxygen, however much oxygen I need, goes to the amount of CO2 I make and the amount of H2O I make. It's a way to do general bookkeeping. And that will allow us to write a general transformation reaction for anything in my resource. So species J, so molecule J, stoichiometric coefficient nu J, whatever the coefficient is, 1 usually, will go to nu Ij Mi, the molecules that are in the atmosphere, however many of these I make per number of these I react. Nu Ij, sum over all the things I make. Okay with that? Really just another way to write a chemical reaction, a reaction balance. Okay, what we're going to do is we're going to take that and use it to write atom balances. So if you think back to that surface, I had boundary work out, I had the work I want to solve for, I think I had heat in, and I had species coming in, carrying a chemical potential, right? But there was a delta Ni coming inside of it. I want that delta Ni. That's the transfer of species I coming in to my system. Well, I can get a balance for that by writing the change of species I inside my system is the transfer, how much came across the boundary, plus the amount I made by chemically reacting all the J species into I species. So there's two ways to do it. If I have a species that's environmental, it can come from the outside, or inside my boundary, I can react isooctane to make CO2 and make H2O. Okay with that? All right. If I do that and do the same thing for a non-environmental species can't transfer in on its own, right? All that's going to happen there is I'm going to react it away. So it's going to go down. Now I can take those two because they're coupled. The non-environmental species make the source term over here for the environmental ones. So I'm going to solve for that, plug it back in, and then flip it to solve for the transfer that comes from the outside. The transfer is the change plus the signed chemical reaction, how much I either make or destroy due to transforming all the J species into I species. Okay? A lot of bookkeeping. We're gonna get there. All right. And note, just in terms of convention, if I have an environmental species present in the resource, it reacts to become itself. So if I have isooctane and oxygen, then the oxygen reacts to become oxygen. Perfectly okay. It's just a way of tracking it. I'll force everything through the chemical reaction term. Okay, so this is what we got. Small amount of work, differential amount of work, reversible, so the best I can do. Comes at the expense of internal energy, can't get at the boundary work, might get a freebie for heat transfer. I can get a freebie from chemical potential of species that come from the atmosphere into the system that are drawn in. So my isooctane will draw oxygen from the outside world. I get its chemical potential. I get to use that. That's available to me. And then the same thing will be true, but for all the species that have to disappear, they will make, by the ratio of stoichiometric coefficients, an additional amount of atmospheric species. Either to discharge, I'll have a minus sign, or to draw in, I'll have a plus sign. Okay, now the neat thing about this, the right-hand side is all exact differentials with constant coefficients, so I can integrate it, and I can choose any path that I want. So this is an important thing in thermo. I don't know if you remember this or not, but exact and inexact differentials. The little squiggly Ds, the delta N's and the rest, those are amounts. Those are inexact transfers, and I have to have a prescribed path to integrate those functions. So work is something that you do, not something that you have. We never talk about a change in work. We talk about how much work you do, and I would have to integrate along a path of doing work to figure out the total amount for that. Whereas energy, I go from here to here in terms of energy. I can do it a whole bunch of ways, but if all I want to know is the difference in the energy, I don't care if you did it by heating, by cooling, by squeezing, then cooling again and doing something else. I just care where I was at the end. Right? So exact and inexact turn out to be really important. Because everything is exact and with constant coefficients, I can choose my integration path through the space. Yes, sir?
I have a question. When you said that you try to transform all resources from I and then
to I.
to J reversibly, to avoid creating or generating entropy. So when they react, even though like they react with O2, the entropy doesn't change.
No, it means that when you actually do the chemical reaction, you have to do it in such a way that you don't generate any entropy. You can do reversible reactions, but they have to be restrained reactions. The easiest way to do a restrained reaction is electrochemically, by either driving it forward or taking electrical work from it. Combustion reactions are unrestrained. And so this is another lecture. There's two kinds of engines. There's restrained engines, there's unrestrained engines. Combustion engines are unrestrained, they always generate entropy. But if I can get in between, and the best example is a fuel cell, that when I take the electrons, the chemical potential of the electron allows me to hold the reaction back. In fact, I can jack up the potential and make an electrolyzer out of it rather than a fuel cell running from hydrogen. But it has to be a restrained reaction. Yeah. Okay, right-hand side is exact differentials, and we have fixed intensive parameters. I can choose the path. I'm going to choose two paths. The paths are arbitrary, but we tend to talk about it this way, thermomechanical and chemical. So we'll do the first integral at fixed composition, so don't change the isooctane inside my system, but we'll take it to the thermomechanical, or what's called the restricted dead state. Dead state is a term for when the resource gets to the conditions of the environment. When it's at the conditions of the environment, you call it the dead state. You've taken everything you possibly can. It's equilibrated, right, for it. So we'll take it to thermomechanical, temperature and pressure of the environment, but no reaction. Then separately, at fixed temperature and pressure, we'll do the chemical reaction part. This will be called the thermomechanical exergy. That'll be called the chemical exergy. And if we do that, what we've basically done is broken it up into two integrals. So from the resource state, what it originally is, to the thermomechanical dead state at fixed composition with no reaction. No reaction means no change in mole numbers, so these two terms are gone. Second part, from thermomechanical state to the ultimate dead state, we'll do the whole thing, but isothermally and isobarically at the conditions of the environment. Okay. So thermomechanical exergy X. Nobody agrees on what to use for the symbols for exergy, so I tend to use X. It's the most generic thing you can think of for exergy. So we'll have a thermomechanical and a chemical part, and the internal exergy of the system will then be the sum of the two. So it was an artificial separation due to the integration path. But don't forget that there's also external or macroscopic exergy from the conservative forms of energy, kinetic energy, potential energy, those that are completely convertible to work. And all the versions of potential energy, not just gravitational, electrostatic, any of the forms, strain energy, elastic strain. So all of those have to be included. So our exergy will be thermomechanical, chemical, and any conservative forms. Okay. All right, thermomechanical. So we'll go from the resource state to dead state, non-reacting. Well, that makes it easy. That'll be delta U, P naught delta V, T naught delta S. So U minus UTM, the original internal energy of the system, minus the internal energy at the thermomechanical state. So cool it down to 25 degrees C in 1 bar. Okay. The pressure of the atmosphere times the original volume minus the volume of the system at 25 degrees C in 1 bar. Still isooctane inside of it, and same thing with the entropy. If I rearrange that, I can rearrange that into U plus P naught V minus T naught S, which is evaluated at the resource intensive state, the temperature and pressure and mole fraction set of the original resource, whatever it is. The extensive composition is the original set of mole numbers. This is extensive. These are big U's and big S's and big V's over here. And this is called the control mass availability function. That's the MIT designation for it, or A, is often used. On the flip side, over here, we now have this at the thermomechanical state, temperature and pressure of the environment, but the original composition, we haven't let it react. Right? It's the first part of the integral. We have the extensive state from the original mole numbers. It didn't react, original set of mole numbers. So I could write this as being A naught, but in fact it's the Gibbs function. It's the Gibbs function of the resource, but at the temperature and pressure of the environment. So we might as well just call it that. Okay, is that right? Okay, so XTM is just this A function that minus the Gibbs function of the resource at thermomechanical temperature and pressure of the environment. Original composition held fixed. Okay, here's the trickier part. The exergy for the chemical part, we're going from the thermomechanical dead state to the true dead state, the reacted dead state, at constant temperature and pressure, but all the terms are in play now. So the first ones are the same. I've got a delta U, I got a P naught delta V, and a T naught delta S. But now the chemical reactions, notice I put a minus sign and introduced a minus sign in here just to stack up the terms down here. Chemical potentials times the change of mole numbers. So integrate the DNI as delta N. Same thing down here, mu naught, stoichiometric coefficients, and the difference in mole numbers. Okay? Mole numbers that I have of species J in the thermomechanical state versus what's left over after all this is done. Okay, if I group that together again, I'm back to the Gibbs function in the thermomechanical state. I have this interesting thing in that I have the environmental intensive state, T naught, P naught, and the composition of the environment, but I have a little bit of a problem. I don't know how many moles of each species are still inside of my system boundary. Now, if we go back to the beginning, if you've looked at a book like Zargat's book on exergy, anybody? There's a distinctly different way to do this, right? And the different way to do this is you construct something that has a bunch of reversible machines that will take the resource until you get it down to the dead state. The tricky part about that, it's just great if you can figure out the path of the machines. It's really bad if you get to the point where you can't figure out where the boundary is and you can't put the next machine in to get you through the path. So the reason for choosing this very abstract path of what's this, put a boundary around it, combine the equations and let her rip, is the abstractness actually frees you from having to figure out how to assemble the machines for this. And this is where it pays off. Because if you're trying to figure out this term, you don't know where that boundary is. Because the boundary has disappeared between your resource and the environment. What it's trying to tell you is that it's not a well-posed question at the end of this, because there isn't a distinction between the two. So that's problematic. But when I come back down here, that's the same term. That unknown mole number set times that chemical potential is that term. And the equations tell you I'm irrelevant. Cancel me out. That's the great thing about the abstract analysis. The equations are the logic are your guide. So those terms cancel out, which is good, and we say, whoo. I say, whoo. Okay, what do we have left? This is the mole numbers of environmental species in the thermomechanical state, but I took all of those and made them all react, even if they react to themselves, so they're all in the J's. So this is just the set of NJs. That's the original composition. It's whatever I've got in my resource. And at the end, all the J's have to have reacted. They can't be around anymore because they cannot be released to the environment. You put all that together, the chemical exergy is the chemical potential of the resource at the thermomechanical state. And this, which looks a little funny, moles of the resource, stoichiometric coefficient ratio between what it will become and what it is, mapping into how many moles of environmental species with their own chemical potential. This is the overall chemical potential of the resource. This is the overall chemical potential of what the resource will become in the environment. So if my isooctane becomes CO2 and H2O, I have to leave behind the chemical potentials of CO2 and H2O at environmental conditions. I can't take that as work. Note too that if, in order to do that transformation, I had isooctane, I had to take from the environment oxygen, because I didn't have oxygen mixed in with my resource, I get to draw that from the environment, and that contributes to my work. I get more work from leaving a hole in the environment by having drawn in chemical potential of environmental species. I mean, that's that resource-environment pairing, right? In fact, you could flip that around. Who says you're the resource and you're the environment? That's just who's bigger, right? Or who's more scarce. Okay, I'll define the last one as script G naught. You can't really write it as G because you got to figure out what the composition is for that. So I'll give it sort of a special symbol, even though it really is a kind of Gibbs function on the back. You can follow that through in terms of definitions. The chemical exergy is the difference between the chemical potential or Gibbs function of the resource before and after it is reacted and diffused to become part of the environment. all at the temperature and pressure of the environment. That's all it is.
So that's not the chemical potential or the free energy change of the reaction?
No, no, it's not. It's definitely not. So if I have a free energy change of reaction, I'd be limited to just the stuff that's inside of my system and the products that it would come to. I could not interact diffusively with the environment or draw reactants from it. But it's absolutely related. So this is a form of free energy. Exergy, for those of you who know free energy, Exergy is environmental free energy. Gibbs function is the work you can get from a chemical system reacting at fixed T and P, but no transport reactions, no transfers across. Helmholtz free energy, fixed T and V. They're not the only two. If I hold S and V constant, the internal energy is a free energy. If I hold S and P constant, enthalpy becomes a free energy. If you tell me that you can make a path that PV to the K equals 17, I can define a free energy for that too. Exergy is literally environmental free energy. Yes, sir.
But if I do a delta G of reaction calculation, usually the delta G means the reactions come in pure and the products leave pure. And they don't react with the environment. So when you calculate the chemical exergy, then what you do is you let those high CO2 concentrations, you try to, in theory, extract work from that. And that would be an example, in my opinion, how the delta G of reaction differs from chemical exergy.
Yes, with one additional caveat. So if I had a mixture that was stoichiometric or lean, say a combustion mixture, stoichiometric or lean, I could use delta G of reaction, take the final composition and do a diffusive exergy calculation into the environment for the chemical potentials. But let me tell you what you can't do, because people try to do this. Go to the rich side. On the rich side, you can't do that because you can't use that original delta G. You've got to make all the intermediate compositions from it. Then you have a problem patching it up and saying, well, so much of this gets to react, so much of this doesn't. Now what am I going to do? So you can get there, but it's easier to get there this way.
But if you're running with excess air, it turns out that that amount of diffusive work you can get out is very small.
We'll get there. We'll get there. Okay, so A minus G naught. And thank you for that because it's small, but it's important. Okay, so let me give you a couple of examples, and then we'll take a quick break. So first, find the chemical exergy of 1 kilomole of methane. Okay, I mean, I want to make sure that you get this, right? And that equation is not the best-looking equation with all the funny summations in it. So 1 kilomole of methane is our resource. I put the equation up in the top. The environmental state, 25 degrees C, 1 bar. My composition, I took 370 ppm. You can tell when I made the slide. 370 ppm of CO2, 3% water, so a little below saturation, 20.3% O2 balanced nitrogen. My resource, so NJ, I have only one thing in it, it's methane. I have 1 kilomole. I have to transform that to environmental species. Methane will take 2 moles of oxygen, make a mole of CO2, and make 2 moles of water. Now in that transformation, over here, it's going to get this oxygen from the outside world. That's going to put a minus sign on its stoichiometric coefficient. So nu is 1 minus 2, 1, 2. My chemical exergy is the chemical potential of methane at the thermomechanical state, pure methane, plus 2 times the chemical potential of oxygen from the environment. This is grabbing a resource from the environment to do this process. But I have to leave behind the CO2, and I have to leave behind the H2O. That's all there is to it. The rest of this, pure, dilute, pure, dilute. Numbers for those who actually want numbers. 830 megajoules is how much work you could get from a kilomole of methane in the surroundings. If you put that on a mass basis, 51.9 megajoules per kilogram of methane. Remember what the lower heating value is for methane? Or higher heating value? It's 50 megajoules for the lower heating value and 55 for the higher. This says that the work you could get from this is a little bit higher than the lower heating value and a little bit lower than the higher heating value. This is part of the reason why people haven't gotten on top of it. It's not terribly different. So you know that there's something not so good about using heating values as a metric relative to work, but it's not so glaring that there's this great arbitrage thing that you should be doing between it. Typically, we'll see that chemical exergy values for hydrocarbons are like 5% higher than the lower heating value of the fuel. Okay, second example. What if I mix the methane with stoichiometric air? So now I've got methane and I've got oxygen in my resource, and I've got nitrogen in my resource. My mole fractions now drop. My stoichiometric coefficients over here. I have the chemical potential of my resource, methane, oxygen, and nitrogen, all at the thermomechanical state. I have to give back my oxygen. I have to give back my nitrogen. They're environmental species, but I get oxygen for free. So I could just as well put in the other two term and cancel these two, bookkeeping. And I have to leave behind the CO2 and the H2O. By doing that, I get 8255 or 51.4 megajoules per kilogram. It was 51.9. By mixing this with air, with stoichiometric air, I devalued the resource. Not by much, but I mixed it in. I dropped its chemical potential. It makes you think a little bit about how you want to treat these things. How about my resource now is not the fuel and oxidizer. I burn that stuff. I burn the stoichiometric amount. So I've got water and CO2 in my system. So now I have 1 kilomole of CO2, 2 kilomoles of water, 7.52 kilomoles of nitrogen. So it's the exhaust products, right, are my resource. New mole fractions. My chemical exergy will be CO2, chemical potential, 2 times the water, 7.52 the nitrogen. Leave behind at atmospheric chemical potential, CO2, water, and nitrogen. Not the same chemical potentials, right? One case the concentration is high, other case the concentration is low. This is the diffusive exergy that you were getting at before. Right? So I still have the ability to do work with exhaust, because exhaust is not at the composition of the environment. Right? How much do I get? 21.6, it's getting small. Or if I try this differently, 1.35 megajoules per kilogram of methane, or 2.6% of the chemical exergy. So it's small, diffusive value. But hold that thought. What if I do the exergy for 1 kilomole of pure CO2? So I have CO2 and I let it diffuse into the atmosphere at 370 ppm. How much work can I get? This is reversible, right? So that's the same amount of work, the minimum work required to take a kilomole that's at 370 ppm and pull it to be pure at 1 bar at atmospheric pressure and temperature. We may think this is small, but is this starting to sound important to you? My resource, 1 kilomole, no chemical reaction required. It's delta mu between the CO2 state and the environmental state. I can write that in terms of the mole fraction, 19.6 megajoules. Or 2.4% of the chemical exergy of the methane. How much was the negligible amount of diffusive exergy left in the exhaust? It was 2.6%. What's the amount of work, minimum work, exergy required to separate CO2 out of the atmosphere? 2.4%. So be careful before you neglect something, because there's enough diffusive exergy left in the exhaust to separate its own CO2 into a pure stream at the conditions of the environment. And if that doesn't make a bell go off in your head about how to design systems where you want the CO2 in its own package, in its own stream, it should. Okay, let's take a 5-minute, we'll take questions and then a 5-minute break.
On that previous slide, what's the nature of the diffusive energy?
Diffusion, just molecular diffusion. So in all of these cases, you have something that wants to generate entropy. Energy wants to disperse. That's the essence of the second law. When you go to take work, the idea is you go along for the ride, right? And what you do is you restrain it in the process of going along for the ride, and that restraint absolutely requires work. That's the essence of the Guy-Stadalla theorem.
The abundance of species in the exhaust, that change in distribution has enough exergy to power the...
To separate its own CO2. Now, that was methane, right? Can anybody see what's special about methane? huge amount of water. So the chemical potential of that water diffusing was enough to separate its own CO2. What if I do it for propane? Not quite enough. What if I leave the temperature of the exhaust not at 25 degrees C, but I warm it up to 50 degrees C? Then it's got enough. Okay, let's take a 5-minute break. It's not just a matter of valuing resources. The interesting part will actually come not just from valuing the resources, but from tracking this through your energy system to see every step of the way inside your system what you did to the resource. Because if the potential is gone, I don't care what you do downstream. You can stack however many machines you want later on inside of it, and the energy is still there, it's still conserved, but the ability to get work out of it has been destroyed. Right, so this is going to turn out to be a very nice metric for thinking about how to optimize energy systems. That really is the key. So a little bit before that, getting a feel for chemical exergy. So methane, significant chemical component. We calculated it at the thermomechanical dead state over here. Goes up with temperature, but you can see most of the bang for the buck, this chemical reaction. If we look at the various products, so these are pure. So CO2, water, oxygen in the atmosphere, but the atmosphere has lots of nitrogen. So nitrogen, not very valuable. Water, more valuable. So it all depends on how much I have. And then if I raise the temperature and the pressure, this is all at atmospheric pressure, then they become more valuable. I pump up that thermomechanical component of the exergy. If you make mixtures from them, so stoichiometric methane air, the products of stoichiometric methane air, and this was what we just looked at, neat carbon dioxide, and the fact that these cross. So that you really do have a small amount that's diffusive, that last piece, but that small amount is the part that we're fussing over in trying to do CO2 separations out of exhaust. Right, so be careful of what you neglect. We'll skip propane air. Not that much fun, propane air products. Okay, this will get to the question about delta G of reaction. So this is just a table, various, mostly fuels in here. The chemical exergy in kilomoles or in kilogram with a specified dead state down here in comparison to delta H of reaction, delta G of reaction, delta S of reaction, bunch of things that you would traditionally calculate and might have tabulated. And the point I really want you to take out of this is that the ratio of the chemical exergy to lower heating value for most hydrocarbons is about 1.05. Now, if we talk about CO and we talk about hydrogen, 0.97, so a little bit on the other side. But it's not terribly surprising that we haven't had, a great failure in the marketplace by using heating values for figuring things out, right? There's a reason why that's been okay. But what I would suggest has not been good is knowing that we evaluate engine efficiency based upon work per unit of heating value, that everybody kind of loses their orientation because they don't really think that's a good comparison to be making. Work per unit of heat, and it's not even heat at the equivalent state that I'm running the engine. So it tends to lead to disorientation about what you should do. What this is telling you is that the efficiency you should be striving for based upon lower heating value is 105%. Now that's not a violation of the first law. It just means we use a silly metric in the denominator for the definition of efficiency. We use lower heating values. Okay, but what it resets is instead of saying, gee, I've got a 35% efficient SI engine, I'm making an HCCI engine that I think I can get to 40, I got a diesel that's running 42, it's running 45, it's running 48.6% over there, we're only getting up to the halfway bar of being a good engineer because the bar's at 105. We've got more to do. And everybody doesn't want to buy that. Say, well, but you've got chemical reactions, you're going to generate entropy, it's really hot. It's in there. It's already there. So the proposition for this is a lot like saying, I wish to sell you an electric motor that is 48.6% efficient. I'm not going to buy it. Okay? And I'm not going to stop until I make a 90% efficient engine demo in the lab. I'm serious about that. 90% in 2030, that's our lab motto. 90% in 2030. It will not be economically viable, I'm quite sure, but I'm going to demonstrate it. For simple fuels, the exergy can be calculated directly. Complex fuels like coal, you can't get the entropy for the coal, so you do it by calculating equivalent mixtures with ideal solution assumptions. It's messy and it's ugly, but you can work it out reasonably well with correlations, but it's not nice. For pure materials, you could actually measure the entropy or the free energy from electrochemical cells, but you can't really do that with coal. The inhomogeneity kills you on that. So there's a little bit of wiggle room in coal and biomass. That was supposed to be the break. Okay, so that was all about calculating. Assumed you had all the properties and could handle it. If you don't, there's something called standard state chemical exergy. If you work less in the combustion and energy systems world and more in the chemi, earth sciences world, where the materials get really complicated, the dead state is the lithosphere, right? That gets tricky. This is a convenient way to go. Standard state chemical exergy and the effective activity from that. Those you can find tabulated in places like Zargat, Morris, and Stewart, various places from that. So that's the other approach that you'll see. For most of the things that you do in the world of energy, you can calculate this directly. You don't need tables, you don't need to be looking this stuff up. It's easy to handle. Okay, balances. So exergy is just a quantity. There's nothing special about this. Most of the time when you talk about exergy, there's this thing of, well, is it a property or is it not a property? It's a property of the system and its surroundings. But if you think about what happens when you actually use data for any system, you have to set reference states for that data, right? If you're doing a chemically reactive system, it's, which enthalpies of formation are going to be 0 at 25 degrees C? Are you going to honor the third law of thermo? The entropy goes to 0 when you go to 0 Kelvin. So by the time you put numbers in, you have to specify external references. So the idea that you have to specify an environmental state is not really a tricky one. If you accept that, then it's a property. And you function with it just like any other property, any other quantity. You write balances for it. So definition, exergy, external or macroscopic forms, conservative forms of energy, kinetic and potential, plus the internal parts. This is the same thing that we do with traditional energy, internal part and an external part for that. If I were to write it in terms of kinetic energy, Ke, gravitational potential energy, the A function we just found, the script G function. If I write a balance, statement of logic, the accumulation is what comes in minus what goes out, plus that which you produce minus that which you destroy. True of anything, just a statement of logic. I'll be right there. In this particular case, accumulation in the system, wherever it is that I'm studying to accumulate, I can have transfers in and out. I have to identify those transfers for the balance. I can't produce exergy. I can only destroy it. And I know that because the second law says delta Sgen is greater than or equal to 0. So I have a destruction, and the destruction is 0 or positive. I have no production. So this is the complement to the second law. In the second law, you say, I can produce entropy, I can't destroy it. So going from a statement, a balance statement, a logic statement to the second law is setting the terms equal to 0 in the appropriate place. Yes, sir? Yeah. Oh, it should be the difference of the squares. You're right. Yeah, that's a typo. Excellent. I'm not going to get candy. Okay, when I get something wrong in one of my codes in class that I have to bring candy for the class next time, packages of Skittles, I'm not bringing you Skittles. Yeah, that's great. That's great. Okay, so balance, all right with that? So we'll destroy it, but we can't produce it. All right. I need the transfers. If I have compression and expansion boundary work, it's P minus P naught, the pressure minus the pressure of the atmosphere. When you think about squeezing something, you're not doing all the work. The atmosphere is doing part of the push for you. Similarly, when you push out against it, you don't get it all. Right? You got to push the atmosphere out of the way. So when the boundary moves, P minus P naught dV. All other reversible work forms, it's the amount of work that you have. If I have shaft work, no dilatation, right? No viscosity. I'm assuming negligible viscosity. That would be the direct transfer. So work is exergy, transfer. If I have heat, I only get the Carnot fraction. So these are all good qualifying exam problems to do. So it's the amount of heat times the Carnot fraction of that. If I have irreversible work, frictional work, it's as though it was heat. You might as well just transfer it into heat and put a Carnot fraction on it. When I transfer matter, This is the exergy per mole, the bar over the top. So that's how much is actually in the matter I transfer times the amount of matter transferred. Plus, I have to push in. This is the same thing as you went from U being the energy in something to H, U plus PV being the transfer of energy when you push it across a boundary. Right? Except it's P minus P naught V because there's an atmosphere there that you're pushing against. When that P and P naught combines with that P naught, the U plus PV becomes an H, and you get H minus T naught S, which would be the flow exergy that you probably have seen. You may have seen somewhere. It's just part of writing the balance.
I'm a bit confused, Chris.
Yeah.
So for Galilean, when it's going through, the system knows only V minus V0. Right?
Yes?
Therefore, the kinetic energy will be V squared minus V0 squared or V minus V0 whole squared.
No, it should be the difference between the two kinetic energies.
But from the Galilean point of view, there is.
Let's set aside rotating. And in the local version of this thing, it should be the difference of the two KEs. We'll talk about this later. Okay, anything else on balance? Yes, sir.
What's the V bar down there?
Molar volume, so specific volume per mole, or volume per unit mole. Molar specific volume, mole specific volume. Okay, let's do an example. This is maybe it's an aging example. This goes back to thinking about the hydrogen economy and making hydrogen from steam methane reforming of natural gas. So we want to make hydrogen, we want to store it, and we'll store it cryogenically. If we're going to store it cryogenically, there's an interesting thing that happens. You've got spin on the protons. Right, so hydrogen in atmospheric conditions is mostly what's called ortho hydrogen. At very low temperatures, it becomes para. So the spin on the protons actually flips between the two states. Okay? So if you have an equilibrium mixture that's at room temperature and you do cryoliquefaction and you do it very rapidly, you'll end up with something that's out of chemical equilibrium that all wants to be para, 99.5% para, but has a huge amount of ortho. There's a latent heat that sits between those two. There's a latent heat of transformation between those. And so if I'm doing a system like this, what I want to do as I'm doing the cryogenic cooling is at every step put a catalyst in there to keep this close to equilibrium and do anything that requires heat transfer at the highest temperatures I can. The last thing I want to do is to be doing it down at 30K. Right? In fact, this was discovered when the hydrogen was first liquefied. And they did the liquefaction problem, said, yes, we have liquid hydrogen, left the room, came back a half an hour later, and it was gone. And it was because the latent heat of that transformation was essentially the same as the latent heat of vaporization. Right? I said, ooh, that's interesting. Got something going on. Okay, so we'll take it as an example. So I've got this, quote, warm hydrogen. It's not very warm, but it's warm relative to 77 Kelvin. Coming into a tank, a dewar, that's got liquid nitrogen. So I'm going to put liquid nitrogen in here, two-phase mixture, 77 Kelvin, 1 bar. I'm venting out to the atmosphere. I'll run through some tubing to get it to temperature. I'll run through a catalyst to do the ortho-para conversion to equilibrate that. That'll be an irreversible equilibration, and it'll have a latent heat associated with it. And I'll come out equilibrated here. I'll pump liquid nitrogen in here just to hold the liquid level constant and replace it as we go. So I want to do a balance. I'm going to do it on a rate basis. The rate of change of exergy inside the cyan boundary with respect to time goes up due to exergy coming in, goes down due to exergy coming out, and it goes down because I can destroy exergy, but I can't make it. So that term will be 0 or positive. I'll destroy it. X dot is actually an amount of exergy per change of time. Fine. If I make this steady state, then I can solve for the rate of destruction is the rate at which it comes in minus the rate at which it goes out. Pretty straightforward. We have 5 transfers. 1, 2, 3, 4, 5. 1 is heat. Rate of heat transfer, Carnot fraction. 4 are matter. The 4 I can write this way or flip it from mole to mass basis, H minus T naught S. Okay. Comment on that. So I write those terms. I have the balance. I can solve for the destruction. It's a matter of getting the properties. Sort of an important philosophical point. if I have something like this, and I connect that line to another system, then I'm transferring Exergy to that system. What if it's not connected to another system? What if it just goes to the outside world? What will happen to that Exergy? It'll be destroyed in the environment. So first, it's a form of environmental pollution because it's exergetic. It's out of equilibrium and it wants to cause change in the environment. Right? And so you really shouldn't credit it. So if it's not actively transferred, it's actually a destruction. And if we didn't include it in this transfer term, if we just took that off, it would just be destroyed. It would show up in our destruction because we'd have that part from the environment included in it. Okay, question for you. How does the entropy generation in that catalyst show up in this balance? Yes. What will happen? Yeah, so I'm going to use more nitrogen from this thing. So that's going to show up by changing the amount of nitrogen, therefore the transfer terms into the system and rearrange the Exergy balance. Okay, efficiencies. So I harped on this a little bit. I'll try to make it clearer what I was harping on. So you all know the term thermal efficiency, which makes perfect sense if you're talking about a heat engine. So if we're talking about Carnot or a Rankine cycle, a Stirling engine, makes perfectly good sense. It's the net work out divided by the heat that you put in. And that's okay, because what you really are doing is a transformation between heat and work. So, I mean, it's not terrible, but it's a little odd, because you're comparing work, which is really valuable, has no entropy with it, to heat, which has a lot of entropy with it. But in some ways, the metric is capturing that. So it really applies well to heat engines, but it already has a flaw in it, because all heat is not of equal value. We were doing the 2 tanks exercise. What if I gave you 2 heat sources? I'll give you a megajoule of heat at 500K, and I'll give you a megajoule of heat at 1,000K. Which do you want? You want the 1,000K. Okay, that's already not in there. That's already a problem, even with heat engines. If we move to chemically reactive engines, it's getting trickier. So what we do is we take that and we try to stretch this by saying, well, let's put a heating value down here. Okay, but now we've got something that really, the energy didn't come in as heat, it came in as chemical bond energy. But not all the chemical bond energy was useful. Part of it has sort of an entropic mortgage from it, right? That's what Exergy is getting at, is the entropic mortgage you have for the energy, or what's called the energy part of it. So what we've done is we've modeled a chemically reactive engine as a heat engine. Which heating value? And why are we comparing work to heat? It's getting even more tenuous. This is often called fuel conversion efficiency. That's one way of sort of straightening it up. But you know, higher heating value, lower heating value, actual heating value, you can figure out what the water vapor concentration is. This one is the one I love. This is John Haywood's from his book, Arbitrary Overall Efficiency. I love it because it completely owns the problem with this. So it's the arbitrary, completely arbitrary, but overall efficiency. Something that's a little bit cleaner is the second law efficiency. So the second law efficiency, eta 2, is the workout divided by the work that you would get if the system were operated reversibly. But what that means is you must define the system, and it must be operable in a reversible way, at least theoretically. Can you think of an important energy transformation that is not operable reversibly? Combustion. Doesn't fit. So you've got to model the engine. There has to be a very distinct model, and you've got to be able to get the process constraints, and it has to be reversible in some incarnation. So it's already a little difficult. But it's great for things like turbine efficiency. So when you talk about the adiabatic efficiency of a turbine, it's how much work I get per unit reversible work for the same model, same inlet state, same outlet pressure. Very reasonable. Exergy efficiency. The Exergy out over the Exergy in. If it's an engine, what we're looking for is work. And the exergetic resource, is there Exergy with the air coming into the engine? And going into the turbocharger, it's got no Exergy. It's an environmental species. right? And even drawing it from the environment, I have to do work to draw it from the environment. So there's nothing that comes with the air, it's just the fuel. So it really is the chemical exergy of the fuel that we're putting down here. But we have something that at least is clean, because we're asking for how much work we get per unit, how much work we could theoretically get from the resource in the local surroundings. Tells us nothing about how we'll actually get it, but now we at least have a yardstick. And that's the key thing about Exergy. It's a yardstick. It's an unambiguous yardstick that you hold up next to your system all the time as you go. And not just a matter of engines, it could be whatever transformation you're doing. I could be making hydrogen from methane or from coal. This is what I put in, that's what I got out, that's how I evaluate. Yes, sir?
Why is it not x out minus x in, so you have the delta things?
So it depends upon how you do this. This assumes that there was not an in, that you did a transformation of some other sort. So when you get into things like cryosystems, you can debate whether you want to have what's called the transference exergy or whether it's the overall amount. For this case, I'm writing the simplest version. And then there's one more. This is sometimes called rational efficiency. And then one more, utilization, which is my least favorite thing, or CHP efficiency, summing the work and the heat that you do per unit of heating value. And that's just a terrible idea. I mean, they're polar opposites, and you can make any number you want. So I really don't like that. Okay. I think we have 15 minutes. Is that right? Okay, so that's what I basically wanted to say, but I've got a bunch of examples that you could be interested in. So things that we could talk about. So you know the West Herman Exergy resources diagram? You might be interested in that and how you get those things, or how you get solar exergy, for example. This is just a comparison of gas turbines moving to NGCC or STIG cycles and watching the exergy distribution and just how you systematically reason across between them. Fuel transformations, air separation, a system with automatic CO2 separation, solid oxide gas turbines. So going towards 70% efficiency, very exciting. Can you ever package it and make it economical? But really interesting in terms of exergy. What you might do in low heat rejection, piston engines, thermal barrier coatings inside of engines. The effect of exergy on environment. Since exergy is a measure of how out of equilibrium something is, if something has exergy and I transfer it to the environment, it will drive change as it equilibrates. And so if you think about it, the objective of the engineer who's trying to get every bit of work out of this system is the same objective as the environmentalist. You want to take every bit of exergy you can out as work. But here's the thing. If John Wyatt were here, he would say, isn't there some point at which it's no longer economic to do that? And the answer, of course, will be true. Right? There'll be some point at which you just can't go after that next little bit. What should you do when you can no longer transform the exergy to work? You should destroy it. Your mission becomes the opposite mission. Rather than saving every bit and trying to get it into work, once you've decided you can't do any more, you should destroy every bit of the exergy you can before you release it to the outside. And if you can't, you'll never get to zero. We can talk about why you can never get to zero. You transform it so that what you release is the most compatible, most easily assimilated transfer of exergy, which usually means thermal, usually means something warm. Chemical is always the wrong answer for that. When people complain about seeing, cooling plumes over, towers and the rest, say, we got to get rid of that. You're nuts. And that's a really nice environmental way to handle the system. Well, just get rid of that. You just violated the second law. That's where the entropy goes. Okay, so that's environmental. And we could talk about optimal architectures. How you use these principles to try and figure out what is the best given a resource and a set of devices. What would you like to talk about? You get to pick. All right. Okay, piston engines. So you probably know that piston engines don't have the highest efficiency. There's a couple of parts to this. Everything that I will say will be about wide open throttle. So it's not about the, we're throttling the engine and being completely ridiculous. I don't like throttled engines. I don't think we need to throttle engines. There are ways to handle that. But if you look at what we have today, This is an energy distribution for a modern canonical gasoline engine. Produce about 10.8 bar of BMEP units of work. We'll produce 10 or 11, typical. If you look at the split of the energy, 37.4% goes into work. This would be like the engine in the Prius. In fact, it sits pretty much right on this point, on the sweet spot in a hybrid. 37.4 you get in terms of work, about 2% in mechanical loss. So we've done pumping, we've done friction, we've included that all, but we split it out. Normally that would be in the heat transfer from it. We pulled it out so you could see it. Heat transfer into the cooling jacket and passive loss radiating off the engine and the amount that's in the exhaust. If I switch from a spark ignited engine to a diesel, but naturally aspirated, a little higher, getting into the low 40s, coming down on the heat loss, overall leaner in the system, coming down on the exhaust, better expansion ratio, running leaner. If I turbocharge that to bring it back up to this, not terribly different. Okay. That's the energy view. And traditionally, this is what we've worked in the engine community. So the old rule was a third, a third, a third. We're a little better than that now, right? A little better than a third, a third, a third. Let's take an Exergy view. This is the Exergy distribution. Same engines, right? Modeled the same way. We're just calculating the Exergy split. Our work went down a little bit, so the efficiency is a little lower, because remember the Exergy is a little higher than the lower heating value was. So 35. Mechanical loss, heat transfer, exhaust, combustion. And that's combustion. I mean, if I do combustion adiabatic, complete combustion efficiency, I go all the way either to equilibrium or take the temperature down and go to complete combustion from it. I'm going to incur about 20% destruction of Exergy because I used an irreversible reaction process. And I did it at relatively moderate conditions. If I take it to some slightly wackier conditions, I can cut that in half, but I'm going to leave that off the table for now. We'll keep compressions sort of reasonable for this. But it makes you think a little differently, right? Because now there's this big pink box sitting at the top that says 20%, and we write it off. So it means that when we start this by saying, well, I can't do anything about combustion, then we're starting out at 80. And now we're partitioning things. And we missed a big box at the top. Okay, if you do that and you say, well, I don't know what to do about that, and you look at this, this is the one that leaps out. You look at this heat transfer box. You look at that heat transfer box. And that's really not good, right? We got to do something about that. And that's the idea of low heat rejection engines. So thermal barrier coatings have been put on gas turbines for how long? 15 years, more? 30 years. I'm off by a factor of 2. We got to do something smarter because this is thermodynamically nuts. And the idea that you're going to put thermoelectrics on the cooling jacket or even on the exhaust system, I'm sorry, is just not a good idea. Because you have a Carnot cap to begin with, and then you have a ZT figure of merit that typically will put you down at 50%, 40%, 30% of the Carnot cap until you get ZTs that are, you know, at least 4 and maybe more like 10. It just doesn't make any sense to do that. We've got to get rid of the heat transfer. If you look at where the heat loss goes, from the gas to the wall, the destruction, this is the overall split of heat transfer. No, this isn't the overall split. This is the split of destruction. Yes, okay. So gas to wall, 46% of the destruction, wall to coolant, and coolant to the environment. And this is important. Going from the gas inside the cylinder to get to the wall temperature, half of the Exergy is gone with that heat transfer. Going from that inner wall to the coolant, another 30% is gone. And the last part is in the radiator. Okay, so that boundary layer inside, which you're going to have, you just got to cut that flux. You need to make this go. How do you split this? If you look at where the heat transfer occurs, so looking at head, ports, valves, liner, and piston, it's a slightly different impression than you might otherwise have. We always tend to focus on there's lots of liner, there's lots of area. But inside the cylinder, the place where it's hot and the surface to volume ratio is really high is up at the top. That's the place where you really care. The place where the velocities are really high, going through the valves, going through the ports from it. And you care about the port heat transfer. You care about it because you want to preserve the Exergy to go to that first piece of turbo machinery And you care about it because coming in, you don't want to heat up the fluid because it kills your volumetric efficiency. So you care about both ports. Those both should have thermal barrier coatings on them. But if you do this, it also gives you sort of another interesting idea of maybe the liner's not so important. You probably know there was a big push by the Army back in sort of 88, maybe 92, somewhere around there, what was called the adiabatic diesel program. So ceramics were coming along. They'd been in gas turbines already. There were all ceramic engines built. Right? It was really interesting. And so cut the heat transfer. There's no such thing as adiabatic, net adiabatic. We can talk about that later. Built these engines, cut the heat transfer, and a couple of interesting things happened. The efficiency went up just a little bit. The exhaust temperature went up massively. Not a big surprise. You didn't have the extraction inside the cylinder. You had to re-architect the system to be able to do it. But one of the really tricky parts about this was handling the interface between the piston, the rings, and the liner. If you're going to make that out of ceramic, you now have a really tough problem because the temperatures are really high, not conventional oils. So you're talking about solid lubricants, you're talking about really tricky things, and funny rings, really, really hard. Okay, but I've never been one to go after 100% of something. I'm always sort of the simple bet, give me half. If you look at this, it suggests leave the liner alone. Go after the valves, go after the head, go after the piston, go after the ports, and use conventional rings, conventional cooling, conventional lubrication down on the bottom end. And so that's what this analysis is. So if you do a low heat rejection engine, so the premise is, I can't do much about this, but you'll notice where we go, we start eating into it. I really want to cut the heat loss. And a reasonable way, maybe a reasonable way to do that, is thermal barrier coatings. Think 2.5 millimeters of YSZ, 8 YSZ, sprayed on all of those surfaces. Behind them, iron, behind them, cooling jacket. So one-dimensional heat transfer there, two-dimensional in the valves, because it's trickier moving up through the heads, and model all that. If you do all that work, what you'll find is you can cut the overall heat transfer in half. It actually cuts the Exergy destruction more than in half, but it cuts the heat transfer in half. Yes, sir? Oh, yttrious stabilized zirconia, the stuff that these GE guys spray on everything.
So that's built in tribology?
Sorry?
That's built in tribology into the material?
No. No, so we're just talking about ceramic coating, right? And on the sides, we're going to keep conventional walls with conventional lubricants, conventional cooling. So no change in the tribology. Yeah. So we're going to let that part of the heat transfer go. Turns out it's actually not that big. So it's not the first thing you want to go after. So if you do that, the last thing you want to do is just make hot exhaust. You have to re-architect the system. And if you do an Exergy analysis, it helps you to think about what to do. You want to turbocharge because the head's going to get really hot. Things are going to heat up. You got to increase the density, keep the power density up. So first, go after a turbocharger. 43%. Exergy efficiency, so you're higher than that on a lower heating value basis, maybe 45 for that. What if we turbo compound? So there's still more expansion in that. So first, take care of your breathing, then actually combine it down in turbo compounding. We're at 48%. We're creeping up on 50%. 50% is my simple answer to sophomores in thermo of saying, you know, at what point are you a good engineer? When your Exergy efficiency is greater than 50%, you're probably diminishing returns. When it's less than 50%, you got more work to do. Embarrassing, huh? It's embarrassing for me. 48%. If we overexpand it, you might ask, what's better, turbo machinery out here or to build a linkage? This isn't quite an Atkinson linkage. It's what's called an X-Link. It's a Honda version of the package, which is really kind of nice. It's compact, and it has 1.4 times the expansion ratio as the compression ratio. The reason why you would care about that is piston cylinder compression and expansion is actually much more efficient. You destroy a lot more Exergy in the turbo machinery than you do if you do it in the piston cylinder. So to the extent that you can package it, you'd rather keep it in the cylinder. So if we overexpand, turbo compound, turbocharge, we're nipping right around 50% for that. And notice the Exergy distribution. All right, so we still got some more in here in the exhaust, but we're pretty well running it down in terms of the pressure. So we're running out of mechanical Exergy, but we still have thermal in here. And we've been nipping away at this combustion part 2 because we're raising the pressure on this system. Right, so we're starting to get part of what we call the extreme states benefit for this.
Is this a diesel engine?
This is an engine that the combustion system is not specified. So it's a 40 crank angle degree wide combustion profile, and we assume that we can make that profile. And that, in fact, is the PhD research of the student, figuring out how to make that combustion process happen. And if you go further than that, if you play out everything you can in terms of the mechanical part of the Exergy, you still have thermal, and you can go after that. You can bottom it, you can steam inject it, a couple of options. 50, I'm not sure which system. This is the steam injected one. This is the bottoming one. You can get to 60. So bottoming Rankine cycle. And you may say, bottoming Rankine cycle, that's crazy. Who's ever going to do it? Cummins is working on how to package it on trucks. GE working on how to package this. Okay, so interesting. The last thing I wanted to say about this is look at this Exergy distribution. 2.8, I'm down to 10 or 8, 3, 1, 5. How am I ever going to get past 60? Remember, I want 90. I want 90 in 2030. Things aren't looking very good. I could do a little bit more here. It's combustion. It's the combustion side. So let's look. That's all I wanted to say about LHRs. Let's look at the SOFC, because that might finish off the story. Yes. Let me do the SOFC, and then I'll talk about the... Ooh, that's a mistake. This will help to pick that up, too. Okay, SOFC, gas turbine, steam turbine, or the infamous triple cycle. So this got my attention. I've been watching this as sort of academic papers for a long time. Oh, yeah, solid oxide fuel cell / gas turbine / steam turbine. I'm going to explain exactly what it is in a minute. I've been watching this as sort of, interesting papers from academics have gone through for a while. And it was the first one that I noticed, okay, 70% efficiency based upon lower heating value, and it seems credible. So it's been kind of fun to watch, and I've been waiting for somebody from industry to say whether or not you could actually make this. Does this actually make any sense? So I get the paper study side of it. This is a oversimplified schematic. I'll show you how we actually modeled it. So natural gas into a solid oxide fuel cell. The air for the solid oxide fuel cell comes off the compressor of a gas turbine. You pre-react in the SOFC. You actually do your fuel transformation in the SOFC. You then combine the anode and the cathode streams, finish the chemical reaction up to turbine inlet temperature, expand across the turbine. It's still hot. Run it through a steam cycle, 3 pressure level steam cycle, and make more power. So this got my attention because it was at a meeting where data from MHI, Mitsubishi Heavy Industries, actually was shown. And their claim was 70 to 74% efficiency. And the interesting part, so this is their 90,000 hours they think they could get. They said they had demonstrated 20,000 hours of durability for the SOFC already, which I thought was interesting. Another one of the things I'd been tracking. And this is sort of the idea behind the plant. The presentation was at the 1-year anniversary of Fukushima. And they were talking about alternative energy strategies in Japan. So the idea of tankers of LNG coming in and building these energy plants to replace the nuclear plants was the theme. But you'll notice sort of an interesting diagram. I'll come back to that at the end. This is modeled. This is work of one of my students, Rebecca Pass. Methane coming in. This says anode recycling on the SOFC. So YSC and SOFC that's doing the pre-reaction. The air is coming from a split gas turbine, so state-of-the-art gas turbine. Coming in through the cathode, we resolve the heat integration inside of it, do a post-combustor from it across the turbine, 3 pressure level, HRSG on the backside. And basically our interest in this is what does it mean to get to 70% LHV efficiency in terms of managing Exergy? What is it about this system that's getting you to that number? So given that the previous example on low heat rejection engines, playing out turbines and overexpansion and thermal barrier coatings and all this stuff, we're capped at 60. I mean, to me, that was the big message. I can't get past 60 for that system. And I got that big old bin of combustion irreversibility sitting up at the top. It makes me go to the other side and say, well, I got to be more reversible. I got to restrain the reaction. Let's go look at the system with a restrained reaction. So that's what Rebecca did. We model this a little differently than from some other studies. We actually do the fuel cell. So we're looking at the exergy destruction along the tube, along the channel inside the fuel cell, the species along it. Here's the VI curve for the cell. This is the temperature matching in the HRSG, the pressure levels on that. So we do it so that we can exercise it, right? We don't want to just grab data from a study because we'll take it outside of its range and then it's not very flexible. And here's the interesting part. If you just look at the gas turbine itself, we're up here around 40 or so exergy efficiency for it. Combustor's destroying a bunch and a whole bunch in the exhaust. Not a big surprise. We put a steam bottoming cycle on that. We take that, we bring that back down again. We're coming up to an F-class system or an H-class system, depending on how you integrate the steam cycles. You go to the SOFC gas turbine, steam turbine cycle. Well, we already took care of that. It was this combustion part that shrunk down. If we're going to get to the really high numbers, we got to do something about that combustion irreversibility. So if you think about this, there's a few important things that happen here. Fuel cells are really nice, but they're really fussy about their diet. They don't like to finish their meal. They don't like high utilization. They like hydrogen to come in. They don't like to go to high utilization. And they're sort of prissy about the temperature, pressure, everything else that you do around them. Combustion is not fussy about its diet. If you overfeed a combustion process, you can make hydrogen, you can make CO, you can make all kinds of stuff out of that might start to look like fuel that you might want to give to a fuel cell. So thinking about these systems and how you interleave these systems to sort of take care of each other's shortcomings. But the most important part is to shift some of that chemical reaction, but not all of it, to a place where per unit of reaction that you achieve, you have less irreversibility. And so that's really what we were looking for out of this. The gas turbine prepares the SOFC better. The SOFC preps the reactants for the combustor better. But by moving 69 to the SOFC, 69% of the conversion occurred in the SOFC and only 3.4% of the irreversibility. Whereas before in the combustion system, it was 20%. So by splitting and rearranging and not saying I have to be a fuel cell, I have to be a combustion system, let's get the best of both, you can re-architect systems in interesting ways. The key is to watch the exergy and just listen to what it's telling you. It really isn't that tricky.
Does that incorporate all of the steam reformation that has to happen on the LNG, or is that a hydrogen-only fuel cell?
No, this is natural gas coming in. So it's internally reformed. It's internally reformed and anode recycled. Right? So you might have a small pre-reforming stage, but it's got a relatively big anode recycle, and we solve across the whole space of that to figure out where the best place is for it. And you break down the methane as you go to keep the concentrations up as you're moving along the cell. You play all the cards. Okay. The interesting thing for that, and I'm hoping GE is going to make this, is I'm sort of reverse engineering this and trying to figure it out, and looked at this and said, oh, this is kind of neat. So looks like some HRSGs over here. It looks like a stack, sort of a gas turbine building. Then I did a calculation on how many tubes you need and how much space you need to put those tubes in at 23 bar to package this thing. I think that's that front building with the cutaway on the side. So it'll be interesting to see how this happens. And I hope it does, because we really do want those high efficiency numbers. And I think that may be our path, is to actually use mixed reaction systems for it. We're 5 minutes over, but I will take any questions. Have I been working through your flags? Did I ignore your flags?
Yeah, a little bit.
Sorry.
The next session starts in 10 minutes.
Okay. Okay, so that's all I was going to say, but I will take questions if you have any. Gary.
Wouldn't you rather have a 70%, 10 megawatt system to put on the distribution side and eliminate 5% transmission loss?
Definitely. Yeah. Well, it's interesting, and you probably have watched this, but the first version I saw of this was like 600 megawatts, then it was 800 megawatts, then it was 1.2 gigawatts, to make me think the economics are just blowing up. So, anything else?
What do you do with CO2?
Yeah, in this particular one, no discussion. But I can show you a system with separated CO2. Okay, yes, sir.
How much is second law efficiency actually used in practice to evaluate alternatives?
So when you think of certain things, when you talk about compressors and turbines, adiabatic efficiency, isotropic efficiency is second law efficiency. I mean, it's our mainstay for how we evaluate those things. When you talk about bigger systems, you've got to pick an architecture, right? A turbine is really simple. Same inlet state, same outlet pressure. That's an HS diagram from it. So it's really easy. It's a simple system. When you get to a more complex system, you've got to agree upon a system and it has to have a reversible limit. It becomes a lot less useful to you. But exergy efficiency, you can still do it because it's about the resource and how you manipulated the resource going through. Anything else? Okay. I'll get you later. Thank you, guys.